Thank you very much for the introduction. I'm very happy to be here in Bangalore at ISC. So today I will be telling you about the conformal bootstrap. So this is a non-perturbative tool which exploits various fundamental physics principles to extract universal features of various quantum systems. So today we will see there will be a wide range of applications of this conformal bootstrap in various branches of physics, mathematics and information science. We'll see how it will help us to figure out and see the quantum features of gravity and to put bounds on the Laplacian eigenvalues on a hyperbolic manifold. So we'll go slow and we will first explore this word, what it means to bootstrap. So if you look up this word in the dictionary, it basically means to promote or develop by initiative and effort with little or no assistance. So we are going to do this thing with conformal field theory. So an example that I would like to give is the game of Sudoku. We are all familiar with this game. You have a bunch of numbers, you know the rules of the game, and the idea is to fill in the blanks. So once you know the rules of the game, we can figure out what kind of numbers cannot go in these boxes, and by ruling out various possibilities, you finally land up with a solution, which is a consistent solution. So in some sense, bootstrap is this game in a sophisticated manner, played in a sophisticated manner. It's basically extracting information from limited initial data using consistency conditions, and this consistency condition in our case will be dictated by nature or the physics. And so this is a powerful non-perturbative tool to compute observables, and I emphasize on this word non-perturbative because most of the systems we will be looking at are strongly coupled, so there is no small parameter in the game, and that's where this power comes in, because even in the absence of some small parameter, we can make some concrete statements and compute observables. And as I was saying, today we are going to use this hammer or use this tool on something known as conformal field theory. But before diving deep into the conformal bootstrap or explaining what conformal field theory is, let me pose some fundamental physics and math questions that we will try to answer using this tool conformal bootstrap. So for next few minutes, I will be explaining some very basic, I will be posing some very basic questions. So suppose someone hands you a quantum system. So what is the most basic yet powerful question that you can ask given a quantum system? And the answer is pretty simple. You want to try to find the spectra of the Hamiltonian, because if you can diagonalize the Hamiltonian, you basically know the system. But the issue is that, like, oftentimes you are dealing with a strongly coupled field theory. There are like thousands of atoms or 10 to the power 23 atoms. So the Hamiltonian is very complicated and you cannot just diagonalize this in a practical purpose. So you need to resort to some new technique to understand the spectra of the Hamiltonian. So today in this talk, we will ask some particular sector of the Hamiltonian. We will ask, given a quantum system, what do the asymptotic spectra of the Hamiltonian look like? By asymptotic, I mean large energy or large speed. So here are three depictions of the energy levels. You may ask, what is the average density of states as you go up in the energy? Whether the spectra looks like this, whether there are arbitrarily large gaps, or whether it is regularly spaced, or whether the spacing goes to 0. So you can ask all sorts of basic questions and ask whether there are universal features in this asymptotic sector of the Hamiltonian given a quantum system. In some sense, yes, in some sense it gives you an asymptotic expansion, but it's not like weakly coupled. Still the underlying theory is strongly coupled in terms of coupling constant. But of course there is an expansion parameter in the large energy and the large speed. Yeah, you can do that. Yes. Most of the system I will be looking at, you can show that the En is unbounded. So looking at n going to infinity is same as large energy. Yeah. I see your point. Yes, exactly. Yeah, so here I am trying to make some broad statements, and later we will focus on that. Yeah. And then why do we care about this asymptotic spectra? Because this asymptotic spectra of a quantum Hamiltonian reveals deep insight about thermodynamic properties at high temperature, which makes sense because you are heating up the system and the high temperature should be sensitive to high energy. And it also cares about it also tells you about the nature of the dynamics, whether, so if you have regular spectra, then the system is supposed to be integrable, whereas if you have very small spacing, and if you see some pattern in how these spacings are distributed, you might be able to deduce that your system is chaotic. So this is important to understand the asymptotic spectra, to understand these properties, the thermalization, the chaos, and broadly speaking, the thermodynamic property of a quantum system. Now, there is a sneak peek into the future. So in particular, we will be answering this question in the context of conformal field theory. So to narrowing down our scope, we will say that we will ask, given a conformal field theory, what do the asymptotic spectra of the Hamiltonian look like? So you should keep this question in mind. Later on, we will come back to this. So now, switching gear, we can ask more fundamental questions about quantum gravity. So can we probe quantum gravity? What are the quantum features of black hole? Can we see the features of discrete black hole microstates, and so on? And it turns out, because of ADS CFT, this set of questions are actually related to the previous set of questions. So if I can answer the previous set of questions, I will have quite a good handle on this. So this is the point, that if you take high energy states in conformal field theory, ADS CFT tells you they are related to the black hole physics. So the point is that if you learn about asymptotic spectra of a CFT, that provides you insight into the quantum nature of black holes. In particular, you can compute the entropy of the black hole. You can figure out in a putative quantum gravitational path integral when do we have a dominance of a black hole saddle. So the point is, once you know some information about the CFT, you can use this dictionary to answer something about the quantum gravity in ADS. Okay. And again, as I was saying, so the first question we will ask is about conformal field theory and the asymptotic spectra. And the second question we will ask, what does the answer imply for quantum gravity? Then we can refine our questions using symmetry. As we all know that. Yeah. You mean given a quantum system, if you go to the long, so here when I am posing these questions, you are exactly sitting at the critical point, and then we are asking about the high energy states on the CFT side. So, and then the way you are thinking, there's a standard StatMach way of thinking, like you will go to long wavelength, then basically the low lying spectra will matter, and then the conformal bootstrap can also answer those questions, like what would be the constraint on the low lying spectrum and how they are related to the critical exponents. Yeah. But of course, these questions are slightly motivated by the ADS CFT, because these high energy states are related to the black holes, microstates, and so on. Yes, exactly. Yeah. So symmetry is our organization principle that we have been taught from very beginning in undergrad. So you can ask a natural question, that how do the asymptotic spectra or any kind of physical observable get distributed among various irreps if you have a global symmetry in the game. And the analogous question on the quantum gravity side is what is the distribution of black hole hairs. And you can also bring in various quantum information inspired quantities in the game. For example, you can ask, what is the entanglement structure of states in a conformal field theory? If we know about the high energy spectra, or some universal features of the high energy spectra in conformal field theory, does that mean something about the entanglement structure of the states? Can we quantify symmetry breaking in QI inspired quantities, in terms of QI inspired quantities, using this universality in the CFT? And you can also ask, how does the presence of a wormhole, for example, break global symmetry? So today, and finally a math problem. As I was saying, that this has also implications in math. So there is a cousin of Riemann hypothesis, which is called Lindelof hypothesis. So the Riemann hypothesis implies Lindelof, but the reverse direction doesn't go. And this is one of the open problems in the math for a long time. You need to show that the absolute value of the zeta function on the critical line is order t to the power epsilon for every epsilon greater than 0 as you go high up in this direction. And it turns out that conformal bootstrap gives you a natural framework to attack this Lindelof hypothesis and make some partial progress. So I will not be going into much details in this thing, but the point is that this question can be studied in the context of hyperbolic manifolds and the Laplacian spectra, and the conformal bootstrap has something to say about it. Okay, so yeah, exactly. So yeah, so here is very important in which window you are doing the averaging. Exactly. It means you can pick epsilon 1, epsilon 2, epsilon 0.1, epsilon 10 to the power minus 30. Any favorite positive number you pick, this statement is true. What is the smallest positive number? Yeah, but there is no smallest positive number, right? Yeah. Actually, the thing is, so people. So I have been told the analytic number theorists are a bit lazy. That's why they do not write log, and they write e to the power epsilon. And if there is a whole zoo of L functions, and for that this is the standard conjecture. Okay, good. Yeah. But if you can prove it for large T limit, for small T limit is trivially true, because order always comes with a capital M, and you can choose your capital M. So if you have a finite range, you can always put a trivial bound, and then for asymptotic it is, yeah. So yeah. Yeah. Yes. So yes, exactly. So if you take limb soup of the zeta half plus it, the limb soup is infinity. Yeah, exactly. Yeah. Okay, good. So as I was saying, my research program basically involves using this bootstrap, a powerful non-perturbative tool, to answer all these questions in the setting of conformal field theory. And I emphasize in a mathematically rigorous way, which basically means that whenever I am making some estimation of the errors of various estimations are bounded explicitly, and we know what we are doing. So every tilde sign and approximate sign you see, they are all rigorous. And to advertise that people from all over the world has participated and invested in this program. So you can see in the blue there are active collaborators from everywhere, and in the green there are some potential collaborators who I interact with, but I haven't yet written many papers. And these are my amazing set of collaborators. Especially I am particularly proud of the first row. They are all the grad students. So Zhengdi has now become a postdoc. He is at UCLA. Elliot is going to MIT. Ishin and Jeha are postdoc in grad students at CALTECH. Indranil is in TIFR. Onshul is a grad student in mathematics department in Princeton. Gordon is at Yale, and Shobik was at San Diego. And then we have a bunch of amazing great postdocs who has also become a faculty, many of them. And in the last row you may recognize many people here. So the bulk of the work I am going to present is basically done with this amazing set of people. So moving ahead, so let me first give you a glimpse of the main results, and then I will dive deep and explain you how these results are obtained at some broad level. So these are the main results. So we basically proved some rigorous theorems about distribution of states with large energy and large spin in 1 plus 1D CFT. In particular, I have shown you 3 different kinds of spectra where you have arbitrarily large gaps, regular gaps, or the spacing goes to 0. In 1 plus 1D CFT, you can immediately show that this first possibility is never possible. You can rule out this possibility by using the consistency condition. And only these 2 things are possible. And you can actually produce a bound on how large this gap can be, which later I will show is basically 1 in some appropriate unit. Oh, they are regularly spaced. Yeah, and the third one is very small spacing. So this is a pictorial description. Later I will show you a concrete inequality. And then you can show that we identified a class of CFTs for which the spectra becomes very dense. So these CFTs are supposed to behave in a chaotic manner, and thermalization should happen. And this, we put out a paper which came today morning in arXiv, so you guys are welcome to look at it at some point. And we also figure out various and all of these results has implications in the quantum gravity. So we figured out the quantum corrections to thermodynamics to the near extremal black holes, and we figured out how the phase diagram behaves when the black hole dominates, when the ADS thermal dominates, by using this rigorous analysis and using these results. So that's one set of results I will be focusing on, and there are various offshoot results coming from this main set of results. If I get to the end of the talk, you will see those offshoot results also. Yeah, no, the spectrums are not bounded by above. Just the spacing goes to 0. It can happen that the spectrum is unbounded, but still the spacing goes to 0. You need to figure out some complicated function. Yes. Yeah, so that's the next level question. So first you need to show that the spacing goes to 0. That gives you a green signal that you can define as statistics. And then at the next level you ask all those questions. So those are kind of future direction to actually figure out the level spacing and to answer how much the modular invariance or all this consistency condition tells something about the level spacing and all those things. Exactly. So that's the direction. No, so that's the folklore, because at some point people figured out all the minimal models for C less than 1, but there is a whole zoo of CFTs for C greater than 1 with only Virasoro CFT, only Virasoro symmetry, and people know almost nothing about that. And all the results we know for those C greater than 1 CFTs with only Virasoro symmetry is coming from the fact you can use crossing, modular invariance, and all these things, to which basically leads to this kind of results. Yeah, exactly. For minimal models and WZW, people know whatever they have to. Yeah, those are all integrables. Oh, the origin of modular invariance is coming from the fact you can put 1 plus 1D CFT on a torus, and if you wait for maybe 10 minutes, I will give you a detailed explanation of how modular invariance comes about in terms of pictures. Just wait a bit. Okay. Now on this side is a blank, so this side I will show you the results about the hyperbolic manifolds. So we established new sharp bounds on the Laplacian spectra on hyperbolic manifolds. So you take some hyperbolic manifolds, you define the Laplacian, and you ask what are the eigenvalues. So if you consider a compact hyperbolic manifold, it's a finite volume. So the first eigenvalue is 0, constant eigenfunction, and then you ask what is the next possible eigenvalue and what is the largest possible gap. And then we can show that the lambda 1, the first non-trivial eigenvalue, is less than this number 44.8883537. And not only that, we can figure out a nearly saturating surface, which is orbifold with the smallest volume, which saturates this bound up to 5 decimal places. So this red digits signify they are actually a surface which saturates up to this point. And for genus 2, you can, so in a two-dimensional hyperbolic manifold, you can define, like you can ask how many holes are there in the surface. So for genus 2 surface where there are 2 holes, you can prove that lambda 1 is less than this number 3.8388976,481. Again, the red digits signify that there is actually a surface which is called Bolza surface, which saturates this bound up to 4 decimal places. And yes. But the point is here we use like 81 crossing equations. So instead of 81, if you do 500, then probably you can do better. Yeah, I am tightening the bound. Are you asking about these 4? Oh, so the previously best, yes. So the previously best known bound was 4. It was from 1980. So we beat basically a bound which was existing for 40 years. Yes. Wait, no. So it lies below this bound because 4 was the previous upper bound. So earlier it was possible, the below than 4 it was possible. Now we are saying it is below than this number. So that's the improvement. Yes, so that's the belief, and in fact right now that's a theorem, because I said this brilliant mathematician, grad student Anshul Adve, he's a Peter Sarna student. So Anshul actually proved a theorem which tells you that if you give me all the crossing equation in the hyperbolic CF manifold context, that uniquely determines the manifold. So that's a 30-page proof of a theorem. I think he is going to publish soon. So actually those people picked up this whole conformal bootstrap machinery because for them it's very precise and they can prove theorems and they can move ahead with this thing. But the point is, you cannot use just one single crossing equation. With one single crossing equation, after some point, it will not converge anymore. It will not converge to this. So you have to use all possible crossing equations. Yes. So, yes, endpoint functions or all possible 4-point function with all external states. Yes. So in the same way that the lower is in the Ising model, you have the island. So if you just use fixed set of crossing equations, then the island will never shrink to 0. Yeah. So as I was saying, previously the base node bound was 4. It was achieved in 1980 by Yang and Yao. And all these results are also very, very rigorous, and it got published in this math journal, Communication of American Mathematical Society. Okay. So these are the main results, and I'm going to explain a bit more in the rest of the talk how we can arrive at these results and give you some flavor of basic ingredients around it. So these are the plan of the talk. So first I will give you a brief introduction to CFT. I haven't really told you what are the rules of the game, what are the rules of the Sudoku here. So I will explain that. I will tell you how we derive the asymptotic spectra in CFTs, and there are some subtext like implication in quantum gravity, there is a refinement, there is a quantum information based idea, and there are thermalization. And finally, in the last bit, I will tell you briefly about hyperbolic manifolds, and tomorrow in my technical talk, it will be all about hyperbolic manifolds. So stay tuned for tomorrow's talk for most of these things here. So is there any question at this point? Otherwise, I will also take this excuse to drink some water. That was the old bound. Oh, no, I don't have any. Yeah, I think it just came out to before. And in fact, it's funny that, so you remember in the quantum mechanics course, sometimes there is a homework problem to put a bound on the first eigenstate or the first excited state by variational principle. You choose a trial wave function which is orthogonal to the ground state. So that's how actually they proved this bound. Sorry, some water. Okay, great. So these are the plan of the talk. So let me start with introduction to CFT. So what and why do we care about conformal field theory? And so the basic statement that we all know that quantum field theory is a framework that describes the physics of the nature, and CFTs are important landmarks or the lampposts in the space of QFT. So it's important that we find this lamppost, because once we find the lamppost, you can see what around the lamppost. And we start a correlation function of local operators. So imagine doing local measurements in a QFT, and such correlation function usually depend on the energy scale and the length scale of the probe. And a standard example to give is the Ising model on 2D square lattice. At high temperature, the spins are all disordered, so there is random jiggling here. And at low temperature, everything becomes fixed to the plus spin or the minus spin. So here the yellow are the spin down, blue are the spin down, spin up. So you have two phases. And if you take these two pictures and if you zoom out, which the technical name of this zooming out is the RG flow, and if you probe the system as a longer and longer length scale, you will see that this becomes more flat and wide, and this becomes more jiggling. And in technical terms, we call it, as I said, we call it RG flow. And what is happening if you are at very low temperature or if you are at very high temperature under this RG flow, the correlation length between these various fluctuation is actually going to 0. And that's what we say, that when we do some measurements, this measurement depends on which length scale we are probing, because the correlation length changes as I change the scale at which we are probing the system. But then a funny thing happens, that there is some particular temperature where under RG flow the picture looks self-similar, and we have long length correlation, and in fact the correlation length diverges. And this is exactly at the point where the scale invariance emerge, and in fact this is exactly at the point where the conformal field theory lives. So CFTs sit at the fixed point of the RG flow. So whenever you see an RG flow, there will be a CFT where the RG flow ends, and it could be a trivial CFT also, or it could be a strongly coupled one. And in technical terms, CFTs are QFTs that are concerned with systems that look same under translation, rotation, and local scale transformation. And as I was saying, in the Ising model case, the conformal fixed point is described by the Ising CFT. So to emphasize it again, the CFTs are important landmarks in the space of QFTs. They describe phase transition whenever the correlation length diverges. So there we have an ordered phase and the disordered phase, and in between them we have a CFT sitting there. And the idea is if we understand CFT non-perturbatively, that goes a long way towards understanding the space of QFT. So we would like to understand the lamppost very well first. And so here is a diagram where we have conformal field theory, and it appears everywhere: statistical mechanics, condensed matter physics, string theory, quantum gravity, and is also an arena to explore various quantum information inspired ideas. So conformal field theories are great, and so we should understand and find these new landmarks or new lampposts in the space of QFTs. So we should play this treasure hunt game to find out new CFTs, or known the observables in the known CFTs much better, or find the universal features in these CFTs. And so what does it mean to understand CFTs? The understand CFTs amounts to understanding the CFT data. And what are the CFT data? So the CFT data normally in a QFT, what does it mean to understand a QFT? You basically understand all sorts of correlation function and how it behaves. So in CFT also you would like to understand the correlation function, all endpoint correlation function. And it turns out that you can understand this endpoint correlation function if you understand this following data. Here I wrote it down, which is basically some list of operators with some scaling dimension delta I and some operator product expansion coefficient, which I callCijk. So if you know this data, you can construct all the endpoint functions in conformal field theory. So the main game is to figure out what are these data are and whether there are universal features in this data. And to explain the operator product expansion coefficient, just imagine doing a Taylor expansion kind of a thing. So you have one operator here, one operator there. You basically put those operators very close to each other, and you can expand them in terms of other local operators. AndCijk are like expansion coefficients. So this is roughly speaking doing like Taylor expansion in some operator space. Okay. So we have a tool. We want to know these universal features of CFTs in the delta i's andCijk. Now I need to tell you what are the rules or the consistency condition. What are the rules of the game, the game we are playing here, the analog of the Sudoku. So the rules are following. Is very basic fundamental physics principle. First is locality. So it basically means in a Euclidean path integral, time and space are on the equal footing. So imagine you are doing a path integral over some complicated manifold. You can slice open this Euclidean path integral in various ways, like this, or this, and insert complete set of states which propagates along the local time direction. So in this way or this way or this way. And the idea is in various ways of opening this path integral in various ways provides you various non-perturbative expansion, and all those expansions should match with each other and should give you the same answer. And so that's our consistency condition. So you will see this thing in terms of torus a couple of minutes later. Now you have unitarity, which basically tells you the Hamiltonian evolution is unitary. And you have crossing, which basically tells you if you consider 4-point function, you can do this Taylor expansion thingy with 1 and 2, 3 and 4, or you can do 1 and 3, 2 and 4. So this will give you two different expansions, but these two expansions should match with each other at a non-perturbative level. And yeah. Oh, because I'm calling it locality because you can locally cut open the path integral, and various ways of cutting it open gives you can insert complete set of states. In a non-local theory, it might not be true that you can always do it. But I guess you are probably asking how it is related to the usual notion of locality. I do something here, and yeah, it's not entirely clear to me. Well-defined path integral. Yeah, I guess you can probably try to extend it in the non-local theories, but definitely there are occasions I know where if you blindly apply this cutting and gluing procedure and land up with result, and those results doesn't hold for non-local theory. So there might be some subtlety about cutting it open and inserting state. Yes, of course for TQFT. That's true. Yeah. I guess to be honest, I have allowed myself some privilege of being a popular talk. I said it locally, but concretely it just means that you take a path integral and cut it open in various ways, and that gives you the same answer irrespective of how that. So that's the consistency condition we are putting in. Yeah. Mm-hmm. Mm-hmm, mm-hmm. Yeah. So yes, so the crossing symmetry is also one sort of locality on the sphere. Yes. So on the sphere you have 4-point function and you can cut open the sphere in various ways. So crossing is in some sense also a locality. That's true. Yeah. Locality in this sense. Maybe I should be careful about using this word. Okay, very good. And then we have symmetry, which basically tells you that there are various global symmetries, which basically implies there are selection rules. And so the upshot is that CFT observables need to satisfy all these consistency conditions, and that means these observables become highly constrained. And a celebrated example of success of Bootstrap is pinning down the 3D Ising model just using these consistency conditions. And here we consider CFTs with Z2 symmetry because Ising model has a Z2 symmetry. And we consider constraints coming from the correlators involving the lowest Z2 odd operator and the lowest Z2 even operator. And when I say lowest, I mean the lowest scaling dimension. And then you write down the crossing equation and you ask what are the implication of the consistency conditions. And you land up with this beautiful graph. So here on the x-axis you have delta sigma, which is the odd scaling dimension of the lowest lying odd operator. And this is delta epsilon, this is the even operator. And you can show that all these white regions are not allowed. So they are ruled out by applying the consistency conditions, and only the blue regions are allowed. And you also realize that there is a kink in this plot, and you suspect that this to be 3D Ising model. So you put in bunch of more crossing equations and zoom on to here, and you see a small island here. And that basically determines the delta sigma and delta epsilon up to some 5 decimal places. So this is a result from 2016. And if we go forward in 2025, in March, this group put out a paper, and now they have determined delta sigma and delta epsilon up to 9 decimal places by playing the same game of putting in more consistency condition. And this is the world record of the best known determination of delta sigma and delta epsilon. Well, it depends. Okay, I will give you the answer what David Simmons Duffin gives you and gives me, and I kind of agree with it. Like if you are experimentalist, you are going to measure something, then you care about the digits. So it matters. For example, precisely the same reason he was doing the precision calculation. Yeah. Oh, you mean whether the experiment precision is related to that many precision? Yeah, I would imagine the experimental precision is much less right now. But you can imagine experimental is becoming more powerful and checking this. But the source of the uncertainty is there is an upper bound and there is a lower bound. Instead of writing it as an interval, they've expressed it as a 2-4. Yeah, no, it's fine. Yeah. Yeah, that could also be a hope, but that's like that's a very hard problem. But depends on who you ask. If you ask Ning Shu, then probably he will say that's a dream he can see. I don't know. I guess I have more faith in the experimentalist probably. Yeah, but
Experiment is boiling water or reducing it. That is an experiment.
Yeah, and conceptually, I think the most important point is that, like, if you are a theorist and if you do not care about the numbers, then this result basically tells you that there exists a unique CFT with a Z2 symmetry, with only Z2 symmetry and one relevant singlet. So that's a very important. Yeah. Yeah. It's completely possible. Yeah, I do agree. Yeah.
I think of it more as hope for giving you leading you towards
I can completely agree with that. Yes. But I guess what I was trying to say, that I have more faith in experimentalists than probably Anindo has. But yeah, but why? But physics is an experimental driven science.
to be fair, personal opinion.
Yeah, exactly. So I am entitled to my personal opinion. Yes. Okay, I'm not commenting on that. Okay, anyway, moving ahead because we need to finish. So you can ask whether people have found new CFTs. So there has been recent progress by Ning Su and Sai Jester, where they found evidence towards existence of CFT with some SO5 symmetry, with one relevant cyclet at something called deconfined quantum criticality. You might want to ask me later if you're curious about what is deconfined quantum criticality, but this will be another separate. So this phase transition goes beyond the Landau paradigm. So that's what I want to mention right now. And of course, I also see this as a monument of success of conformal bootstrap. The best known bound on the Laplacian eigenvalues of the lower genus hyperbolic surface comes from our result using conformal bootstrap program. Okay, so far I told you about the numerics, but the point is the consistency conditions are also powerful analytically. So for the rest of the talk, I will mostly focus on various analytic results. How much time do I have? Okay, I see. Running really short of time. Okay, I'll try to. Okay, then it's good. Okay, so we'll come back to this question that I posed earlier, that given a conformal field theory, what do the asymptotic spectra of the Hamiltonian look like? So there are 3 diagrams. Now we will explore an analytical example in 1 plus 1 DCFT, and we will first try to make a statement about the average density of states. And to do that, I need to tell you some basics about 1 plus 1 DCFT. So this you should take it as granted. So in 1 plus 1 DCFT, conformal symmetry gets extended to infinite dimensional symmetry algebra known as Virasoro algebra. It comes with a number which is called central charge C. You will see this number C appearing everywhere in the game. And the ground state energy of a CFT on a spatial circle is minus C over 12. So this is also fixed by the Virasoro symmetry. So these are the 3 information you should keep in your head, and we will go ahead. So we will show that how the central charge for 1 plus 1 DCFT, if someone hands you this number C, how unitarity and locality implies a universal formula for 1 plus 1 DCFT known as Cardy formula. So this Cardy formula is about high energy density of states on average in 1 plus 1 DCFT. So as you go up, what is the average density of states for these CFTs? So high energy means high temperature. So we should be looking at high temperature behavior of the canonical partition function. And this is exactly where I am going to explain to you how the modular invariance comes in. So we take a 1 plus 1 DCFT. The spatial circle length is twice pi. So these green lines are identified. So this is a circle. We heat it up. So the Euclidean time circle becomes beta. The thermal circle length is beta. So we have a torus, spatial circle twice pi. The time circle is beta. And basically we are doing is to compute the canonical partition function, we are doing a path integral over a torus to compute this thermal partition function. So now I said that I can have this torus and I can cut it open as I wish. So initially the time was going this way, but now I cut open the path integral along this dotted line, and I let the time flow from this way, from left to right. And if we do this, that amounts to swapping the space and the time cycle. So instead of this diagram, you have this diagram. So now beta becomes your space and twice pi becomes your time. So now you want to take this picture and you want to superimpose on this picture. You do that and you see, oops, it do not match. The spatial length circles do not have the same length. So you cannot really compare with each other. But now you remember that you are dealing with a CFT, conformal field theory. So you are allowed to scale the space and time in the same manner. So you take this picture, you scale by twice pi over beta. So now this beta becomes twice pi, and this length becomes 4 pi square over beta. So once all the dust settles, what you have derived, that your initial torus path integral with time circle where the length of the time circle was beta is same as the another path integral where the time circle becomes now has a new length which is 4 pi square over beta. So by doing this simple manipulation and the fact that things are scale invariant, you have shown a duality between beta going to 4 pi square over beta. So as you take beta small, so high temperature, the 4 pi square over beta becomes large, so this is a low temperature. So what you have derived is a high temperature, low temperature duality. And in technical terms, this is exactly what we call modular invariance. So this is how modular invariance comes into the picture for 1 plus 1 CFT. And once you have this modular invariance, you can, because, okay, so this is basically the S transformation. So if you define the modular parameter tau as twice pi I tau equals beta, then beta going to 4 pi square over beta is exactly tau going to minus 1 over tau. And there is another generator capital T, which basically tells you that you are dealing with a bosonic CFT where all the spins are integers. So in our result, the fact the spins are integers will not matter at this point. So I will forget about T for now. So I am only demanding invariance under S. That's enough for now. Yeah. Yeah, so the modular group has two generators, S and T. So this is S. Yeah, it's a yeah. Much bigger, yes. Whatever you can generate with S and T, yeah. Yes. The whole modular group. Oh, the. Yeah. Yes. Right. Yeah. Yes. Oh, I see. But yeah, I guess then you have to go a little bit abstract, because then you have to. So here we are dealing with a square torus. You can consider a tilted torus, and this tau goes in a complex plane. And then basically you can think of this torus as you have two basis vectors and you have some identification. And this identification doesn't care about which basis vectors you pick, and you can go to other basis vectors and.
Describing in words how we do the modular transformation.
Yeah.
Question is, what does it mean?
Yeah. I guess Chetan is saying that if you know S and T, you basically know everything. So if you give some physical description to S and T, that's your job is partially done. Yeah. Anyhow, so we have this beautiful equation, z of beta is z of 4 pi square over beta, and we want to extract physics from it. So how do we extract physics? You take beta going to infinity, so log z goes like this, minus beta times minus c over 12, because the ground state energy is minus c over 12, I just told you. You do use this relation, you go to this side, you basically exchange beta with 4 pi square over beta, and log z becomes this expression. Once you have this expression, you basically rewrite it in terms of this equation, where on this side you have the canonical usual expression of the canonical partition function, and in this side you basically use this information from the left hand side, so you have a universal expression. So this is nothing but a Laplace transform of the density of states, and to extract the density of states you basically do an inverse Laplace, and once the dust settles you get this beautiful answer which was derived by Cardy. So this is a universal high energy density of states known as Cardy formula. And the important point is it is controlled by a single parameter, which is central charge. It appears in the entanglement structure of vacuum states. It also appears in the black hole entropy and the microstate counting. So this is one of the classic examples where you can see that the modular invariance gives you this universal formula is only determined by a single parameter. You do not need to know how the Hamiltonian is or what system you are looking at. So to refresh, you have this CFT observable, you satisfy various non-perturbative consistency condition, they become highly constrained, and there is an emergence of universal features. So my research arena is based on this conformal field theory, So I basically use various tools from analytic number theory, numerical techniques like linear programming, then thermal effective field theory to figure out these universal observables in conformal field theory. And of course, this has implications in the quantum chaos, thermalization. There is an interplay of symmetry and entanglement. There is an implication in quantum gravity and black hole physics. There is also implication in hyperbolic manifolds, which has other offshoot results in Euclidean CFT, QFT in de-Sitter, and again, you can think of hyperbolic manifolds as a toy model of quantum chaos. So this is the big picture of the things I am interested in and I have been doing. So these are my research targets. So I have been telling you again and again that there are consistency conditions. So the broad question you want to ask, what is the space of solution to the consistency condition? What are the universal features? What is the space of chaotic CFT? What is the space of holographic CFTs? By that I mean that what kind of CFTs exhibit the features of Einstein gravity? So these are the broad questions. And I have been developing new analytical tools to systematically study the constraints satisfied by the CFT data. I have been using numerical tools like linear programming. And then I have been building bridges between physics and mathematics. There is a growing interplay of harmonic analysis and CFTs, spectral geometry, and Tauberian theorems in my research. And so using these tools, we would like to carve out the CFT landscape. So this is another picture I would like to very much show that. So this diagram is basically taken from inspired from a paper by Luca de la Cretes. So in CFT you have operators, they have some scaling dimension, they have some spin. If you have global symmetry, they have some charge Q. And then you can probe various regimes in this plot and ask what are the universal features. So if you want to know large delta, you use this analytic number theory technique called Tauberian theorems. If you want to know about large spin, then you use something called light cone bootstrap. If you want to know about large charge, then you can write down some EFT to describe the universal physics over there. And over the years, I have written papers in all across these branches to figure out the universal physics in various corners. And you can ask me later what are the specific results and so on. Given the time, I will not be able to cover everything. And near the origin, the numerics is more useful for the low-lying spectrum. And I have also written papers for this numerics in the context of hyperbolic manifolds. So now coming back to the question, the first research target, what are the universal features of the CFTs? Yes. Yeah. Yes. Yes, that's a very good question. So there is no unitarity bound. It turns out that the EFT only works where the ground state energy goes like some power of Q. So you can, there could be theories over there, but this EFT cannot access that. And also depending on so I only wrote it in this axis. You can go along this spin axis, and then also you need to change the EFT. So at some point, first it would be some Goldstone bosons like thing, some pions like structure which will carry spin. But at some point that EFT will break down, then you will have some vortex-like solution, and so there is a whole picture. So I think Zohar and Gabriel Cuomo has been thinking about this in recent days. So I thought about it in a couple of years back. But yeah, so there's a very beautiful story about this and also going off this axis. Okay, good. So what are the universal features of the CFT? So there is this Cardy formula which is controlled by the central charge, I already told you. And in higher dimension you can also write down similar formulas using thermal EFT. But these formulas has a problem, because I am telling you this is the average density, but I am not telling you whether what of these three possibilities are possible. And in fact, if you are very careful, you would have asked me that the CFT has a discrete spectrum, it is a distribution. How can you approximate a distribution with a continuous function? And this is not possible. So Cardy formula is basically a continuous approximation of the distribution. So you want to understand this approximation better, and in the process of understanding it, you would hope to understand about these three possibilities and which one is possible and which one is not. So we would like to do that. So, yeah. These are. Sorry, say that again. Yeah. The number of states are unbounded. Yeah. So we would like to have a refined answer to this question. How this density of states behave. So the standard thing you do, you take the density of states, you integrate over some small window function, and you want to estimate this integrated density of states, which basically counts the number of states in that window. And so we did that in these two papers, and you arrive at this beautiful inequality by doing this procedure. Yes, delta is related to energy. Yeah. So energy is basically delta minus C over 12, to be very precise. So C is the central charge. Yes. Yeah. Yeah. So this is the precise mathematical inequality we prove. So let me unpack this a little bit for you. So on the top, you see in the numerator you have density of states integrated over this window. So it counts the number of states. This rho 0 is the Cardy's prediction, which is the average density. So roughly speaking, you would think that this ratio behaves like the size of the window, and this intuition is true. And in fact, you can show that this is upper bounded by the window size, which is twice little delta plus 1. And in the same way, in the lower side, you can show that it is twice lower bounded by twice delta minus 1. And all this pops out from the modular invariance. Mm-hmm. Yes, yeah. Yes, so the point, yes, exactly. So for the partition function, you deal with the Dedekind eta, which has modular invariant covariant property, and the Dedekind eta. And from that you can derive a formula. In fact, there you can do better, because you know that is basically the Q expansion, the analog of deltas are all integers, so they are holomorphic. So you can write down a Rademacher expansion, which is a convergent expansion. So you not only know the asymptotics there, you actually know a full convergent expansion of that. So you can do much better in those cases. And in fact, in holomorphic CFTs, for example, monster CFT, you can also do that. But here the idea is we want to make statements which is true for all CFTs. No. Oh, that's that's related to something called monster group. So it's the largest sporadic group, and yes. It's a very nice name. Okay, so now from this inequality, I claim that we can derive something about the asymptotic spectra. So if you take a window size bigger than 1, that means the lower bound is positive, which basically means that there has to be some state inside this window. That means any window you pick which is slightly bigger than 1, there has to be some state. So that means the gap cannot be bigger than 1. So you immediately show the lim sup, this difference is less than equals 1. So this was first conjectured by a paper by Bauer and Shasha Jibayadov, and then we proved it with my friend Ganguly, who is actually an electrical engineer. And yet another proof came from another paper written by me and Bauer in next year. And it basically shows that there doesn't exist any unitary modular invariant 2D CFT with sparser asymptotic spectra than this. So pictorial, yes. So there are standard Tauberian theorems, but the point is we cannot use some theorems directly. So we learn the techniques, and then we adapt those techniques and modify it for our need and prove our own theorems. Oh, most of the Tauberian theorems are about window size which goes from 0 to delta, rather than this kind of microcanonical thing. Yeah. So the other things goes from 0 to capital delta. So the size is very, very big, and in the microcanonical setup, you want the window size to be small. So you cannot use those theorems directly. Okay, so that basically, because there is a bound, it basically rules out this possibility. That was the first result I showed you. So there are only these two possibilities are left and allowed. And in fact, you know that these possibilities are actually mostly happens for rational CFTs, and even for the Dedekind eta thing, the partition of the integer, even though that's not a CFT, but that's a modular invariant function, so you can do that. Okay, so you can refine these results in various ways. So in the 1 plus 1D, you have the left movers and the right movers. So you have left moving energy H, right moving energy H bar. These are the fixed spin lines, goes along the 45 degrees. So these are the spins, and you can prove many results along this direction. For example, there is a Cardy formula for H bar going to infinity, which basically proven by this on this paper with its grad student Zhengti. And then we can prove a result along these fixed spin lines, and we can derive bound on asymptotic spacing on each spin sector. And we can show that this picture I just showed you is also true for every spin J in the CFT, not only for all spins, every spin this has to hold. And then the next question we ask, can we capture this for some class of CFTs, whether we can distinguish between these two? And the answer is yes, we can distinguish. And again, as I said, the paper came out today morning, and we can show with Balt and Jashin that the large spin spectrum is dense for CFTs with Virasoro symmetry only. This, let me just give you a brief overview. The point is that you have these two H and H bar, and there is some spatial lines which is C minus 1 over 24. From the gravity side, this is related to some black hole threshold, and the point is if you are on the left or if you are on the right or the top of this line, and if you go up, the spin increases because the spin lines are 45-degree lines. So as you go up, the spin increases. As you go this way, the spin increases, and you can show that irrespective of the size of the green window, there has to be Cardy number of states, and there has to be universal growth in this thing. So that basically tells you the large spin spectrum is dense, and you also prove some uniformity. So this result has to be proven with some degree of uniformity, and from there you can show that the spacing between operators at large spin has to go to 0. So you basically land up with this scenario where instead of this direction being the energy direction, now this direction is the spin direction. So in the large spin limit, the energy levels basically goes to 0 for this particular class of CFTs where you only have Virasoro symmetry and nothing else. And this should be the candidates for CFTs which are chaotic, which thermalize, and in the large central charge limit, this should be dual to the Oh, the statement is the following. So you have H bar, and so you have the fixed spin lines. Maybe I should draw here. Maybe I should have drawn a better picture. So you have this thing, you have fixed spin lines like this, and then you pick some lines like this, and you count number of operators in this interval. And the statement is, even if you just shrink this window as j to the power minus 1/4, as you go up, even then there has to be Cardy number of states. And that immediately implies that the spacing between operators on each of these lines for sufficiently large j has to go like j to the power minus 1/4. So in any bounded interval above the threshold, the spacing between operators with spin j goes to 0 as j goes to infinity, at least as fast as j to the power minus 1/4. So that's the theorem we prove in this paper. Yes, to the morning. Yes, there you do not have if the first condition is not satisfied, because it's not only Virasoro symmetry. Yes, so so you can say, so you cannot apply this result for those kind of CFTs, but then the idea, they are not chaotic, but there is a so the point is, here we impose a twist gap with respect to Virasoro symmetry. If you have supersymmetry or bigger chiral algebra, you need to impose a twist gap with respect to the bigger chiral algebra, and then play our game. And if you then play our game, then for WN CFTs, for example, I believe this threshold will be C minus n minus 1 over 24, and then you can possibly prove similar results. There will be some shifting because of extra symmetry or extra currents. So roughly speaking, what happens, you show that in some particular limit where you take beta L to 0 and beta right to infinity, the vacuum dominates. So basically, when I say vacuum dominates, I should basically say all the twist 0 states dominate. So if you only have Virasoro symmetry, then the only twist 0 state is a vacuum. So you have vacuum dominance. Otherwise, if you have bigger chiral algebra, then you have to collect all the twist 0 states in the vacuum module, basically module of the.
They also can be chaotic.
They can also be chaotic. In principle, they can also be chaotic. Yes. If you go away from, the free point, I think it's supposed to be chaotic. Exactly. But I think doing explicit computation will be very hard, really going away from the free point. Okay. So the point is that consistency condition imply universality. I already told you these two answers. So check mark. So these are basically features of discrete states of black hole microstates, because I can tell you about the level spacing now. And we can extract more refined information. So just to go over quickly, I already told you about the spin projections. I have results for every spin. So you have global symmetry. You can ask, you have results for every irrep, density of states projected onto irrep, and we can derive similar bounds. And this ratio where rho alpha over rho, where rho alpha is the density of states projected onto irrep alpha and rho is the full density. This basically goes like d alpha square over g, where these are group theory quantity. And again, this result can be written in a more precise way, which I haven't done here, like some form of inequality. Oh, I should finish up? Yeah, 5 minutes, okay. I can do it in 5 minutes. Okay. Yeah, okay. Yeah, I can do it in 5 minutes, okay. Well, I am happy to give, but I don't know whether people will enjoy it. I can go on for 6 hours without any stop, I think. So the point is just the big picture. This also gives you some information about entanglement structure and some symmetry resolved Renyi, and it tells you about the symmetry breaking in the QI inspired quantities and so on. And you can also make statements about ETH, or energy eigenstate thermalization hypothesis, as I was saying. So roughly speaking, it tells you, ETH tells you the individual eigenstate should behave thermally. So if you take some matrix element of some light operator in some high energy states, it should behave thermally. And that amounts to proving some statements about OP coefficients, the Cijk on the CFT side. And you can actually do that. So there are a bunch of results we proved. So the density of states comes from the partition function, and all these OP coefficients come from looking at 1 point, 2 point, or sphere 4 point functions. And yeah, and a couple of these papers are written with Shovik, who was a grad student here with Justin. And then I guess I don't have much time, you can discuss the implication of these results in quantum gravity. So there has been some conjecture long back into 2014 by Hartmann, Keller, and Stoica, which basically says that how the phase diagram looks like in the quantum gravity in ADS3. So you have left moving temperature and the right moving temperature, and the statement is that except for this cell dual point, you have a black hole phase on this side, you have the thermal ADS phase on this side. So this was a conjecture from HKs, and they provided some numerical evidence. And we proved this conjecture with Indranil, who was a grad student at TIFR, and Jaishin Chao, who was a junior postdoc at EPFL. HK is Hartmann, Keller, and Stoica. So it's a paper from 2014, where they first proved this usual result of Hawking phase transition at beta equals twice pi. Then they turn on angular fugacity, and then they basically do some numerics to give a hint that and conjecture that this should be the picture on the CFT side, and then we can use modular invariance very carefully to actually prove this statement. And the key ingredient is that you have to assume the spectrum is sparse for low twist, not only for low scaling dimension. The sparseness is very important, and that's what I was mentioning to Pratik the other day. Yeah. So we proved this conjecture in last year in October, and this is the picture. Oh, the color has changed somehow. Okay. So this is the black hole phase, this is the hyperbola, beta L times beta R is 4 pi square, and this is the thermal ADS phase. And this result also tell you about some how the near extremal black holes obey thermodynamics with appropriate quantum correction, and there is a whole story of how you can relate this story with the Schwarzschian limit and the JT gravity and so on. And so I already told you about this. And so far we have mostly focused on 2D. We can also do in higher dimension. We can develop some notion of high temperature, low temperature duality, and this has implication of universality of Renyi entropy and thermal effective field theory. So we put out our paper last year and recently in March, which has application in the Renyi entropy. And so I have told you about this, and in the final minute I wanted to spend some time about the hyperbolic manifold and CFTs, but I can probably postpone it for tomorrow. And they are the main punchline, as I was saying, that you can prove results about the Laplacian spectrum on these manifolds. So this might seem to disconnected topic, but it is actually not. They are related, and they are related because the isometric group of the hyperbolic manifold is SO1, D, which is the Euclidean conformal group. So you can prove, and these are also chaotic models. So these are models where you have quantum chaos with conformal symmetry. So you can prove bunch of results. I'm not going into details now. We can also, Yeah. It's you have to compactify, because otherwise the spectrum would not be discrete, and there's you need to, so otherwise the question wouldn't make sense. Yeah, exactly. Yeah. That's the play. That's the game we play. We quotient it, and we give in the information about this gamma in various ways inside the Bootstrap program. I will be explaining this tomorrow in great detail. And there is a nice connection, because you have Cardi formula, you have Weil law, you have Cardi-like formula for OP. There is a bound on L function. There is the existence of isolated CFT, which is related to the rigidity of manifolds. So the summarized consistency conditions are important. They are powerful. They lead to universal features of high energy and low energy data in conformal field theories, and it is an exciting time to be bootstrapping. And these are some of the future directions I want to explore, all based on this conformal field theory. So you want to chart out the holographic CFTs, quantum gravity in ADS, ensemble average, and the hope is you can make statements which are precise and mathematically rigorous in this setting. And you can also probe chaos, thermalization, you can explore the connection with harmonic analysis. And then there is a synergy of spectral geometry and CFT, which is related to conformal measure space. Don't worry about these terms, I will explain tomorrow. And there is also, you can, as I said, there are various QI motivated quantities that you can nicely compute in the CFT setting. So I also want to explore that direction. So with this, I end here, and I give you this picture again and say the conformal bootstrap is great. Thank you. Yes. That's an excellent question. So for d greater than 2, indeed there is some formulas where you can look at fixed mean large delta, and you can write down average density of states. But this cannot really distinguish between these three cases, whether you have arbitrarily large gaps or regular spacing, or so there is no rigorous formulation of this question in the higher dimension. In 2 dimension or in 1 plus 1D, you can do things because of modular invariance. You can estimate all the error terms. So roughly speaking, you should have this picture that so you have the modular invariance, you go to dual channel, the vacuum dominates and gives you the average density, and then you have bunch of error terms. So naively we say that each of the error terms are individually or exponentially suppressed, and so we say we are happy. But the point is there are infinite number of such terms, and there can be resummation effect, and in fact this resummation effect controls the size of the window. So in 2D, because of modular invariance, even though there are infinite number of terms, you can use this modular invariance in like a multiple ways, multiple times, to estimate this resummation effect, and that translates to some statement about the spacing. In higher dimension, you only have thermal effective field theory, which gives you the leading answer. But to estimate the non-perturbative correction is beyond the standard knowledge we have right now, but maybe it's possible in future. Yes, somehow there is a huge jump when you go in terms of mathematical rigor when you go from 2D to 3D or higher D. Yes. Well, how do we know that physics do not care? Because I object to that statement, because earlier people used to make some prediction, you go to experiment and you prove things, and then you can match. But now we are making some statement about black hole entropy and no one is doing an experiment. So how do we know that we are doing things right? But I agree with you that we should be open-minded and explore things. Yes, of course, I do agree with that. And I do think that, for example, this harmonic analysis thing, the L function business, I think one can make more statements, and people have been making some statements regarding chaos and going beyond that. So the idea is that this gives you a sense how the leading answer is true in which average sense and how the spacing is. And all the information about level spacing and chaos will be a fluctuation over this average answer. So once you have this thing completely rigorous, then you can talk about this fluctuation. So, Oh, spin is 0 and then you go to delta proportional to C. You can make some, so we can make, this is somewhat complementary to that regime. Yeah, in fact that's an open problem. Like first we want to show that the spacing really goes to 0 in that limit. That would be amazing. That. Yeah, it should be possible, and then you probably have to bring in this harmonic analysis business. So people have been thinking about that, like Eric, Paul, Motor, and Gabriel, and I also have started reading about it. So I think it should be, it should be possible to explore that direction, and I do believe it should be possible to make a rigorous statement. So it's just that you have to wait. For example, this spacing going to 0 limit, I have been after this result since 2019, and like only been able to prove it like very recently. So maybe we have to wait a bit, but things will happen. Yes. Yes, you don't have, yes, exactly. So that's the problem in terms of making a rigorous statement, but then we should keep our mind open and do thermal effective field theory and prove results. So my philosophy is, as long as you can be rigorous, you should be rigorous, but if you can't be rigorous, then you should not stop thinking about physics. So then you should go ahead. So that's the philosophy in higher D right now. Okay, thank you very much.